Welcome to the lecture on finite element analysis. In the last lecture, we have introduced the first few steps of finite element method. One is the discretization of the structure, in which we have divided the structure into number of elements based on number of guidelines. Then we have selected the displacement function over each and every element that we consider. We have just assumed the variation of displacement using polynomials. Then the third step is calculation of element properties. We have concentrated on the derivation of element stiffness matrix, and we are going to discuss the derivation of B matrix, and also I will tell what is D matrix, etc. We will discuss. The next step is, this is for one element. For each and every element, you may be considering different types of elements in a single structure. The single structure may consist of line elements, triangular elements, and also, so for each and every type of element you have to derive the K matrix, element stiffness matrix. Then you have to get the element load vector. Element load vector, whatever is the load that is given on the structure over each and every element that is considered. Maybe a line element, maybe a combination of the structure may be consisting of a combination of elements, maybe line element, triangular element, quadrilateral element, whatever it may be. For each and every element, from the load that is given on the structure, for each element you will have to convert the loads as nodal loads. If you consider 4 nodes, if you consider only one displacement, so you have to convert the given load at the 4 nodes of the element in the given direction, in the assumed direction or given direction. That is what is called getting the element load vector. So these things already we have discussed, therefore I do not repeat. Therefore, for getting the load vector, we have got, one is the direct method, one is the direct method. The direct method is also called lumped load method. Lumped load method. In lumped load method, you have got method of inspection, method of inspection, method of equivalent joint loads. Method of equivalent joint loads. The second method is that of the variational method. Variational method. The variational method will use the formula equivalent joint force is equal to over L n transpose F into dx. This is the formula. This is for a linear element, one dimensional element. Equivalent joint force is equal to integral over the length. N is the shape function. We will discuss what is a shape function, how to derive the shape function, and what are the roles of, what is the role of the shape function in getting the element stiffness matrix, in getting the element load vector. All those things we will discuss elaborately. Now we will complete the basic steps to start with, right? So N transpose, how to derive, we will discuss later. Into F, this is the force on the structure, F into dx elementary length. If it is a one dimensional element, this formula can be used. If it is a two dimensional element, you have to integrate over the area. This will be dA. If it is three dimensional element, over the volume into dV. That we will discuss later. This is for a simple line element. This is the formula. These are the different methods of getting the element load vector. Element load. So that is the next step. Next step is getting the element load vector. getting the element load vector. Now, so far we have divided the structure into number of elements. We have assumed the variation of displacement over a single element. Then we have derived the element stiffness matrix for a single element. We have obtained the nodal load vector for a single element. The finite element method follows the approach part to whole. Normally in surveying we use to discuss with the whole to part. Here part to whole. That is, you analyze a part, that is each element, then assemble them to get it from the structure. Part to whole. Therefore, the next step is assemblage of a global stiffness matrix. Now only we are going to the structure. Assemblage of global stiffness matrix capital K. Element stiffness is small k. Getting the value of capital K and global load vector F. Because for the structure it is capital K into U equal to F. Now already we have got small k. For elements we have got, for element it is delta, for element it is P. This we have got it. We have got small k for all elements and also small p for all elements. So this we have got it in the third step, this we have got it in the fourth step. Now we have to assemble these values. For individual elements you have got the value that you have to assemble for the total structure, and then we have to get the global stiffness matrix and the global load vector you will have to get. For this, what we do is we are going to follow what is known as direct stiffness method. We are going to follow direct stiffness matrix because when you take a beam, we have divided this into 4 elements, let us say. Let us say this is element number 1, element number 2, element number 3, element number 4. Now, when you take two nodes for each element, this will be of size 2 by 2, this will be of size 2 by 2, 2 by 2. If you assume only one displacement per node, it is 2 by 2. Now, when you take the total structure, here there will be one node. This is node number 2, this is node number 3, this is node number 4, node number 5. Now, for each element, you have got assuming only one displacement, it is 2 by 2, 2 by 2, 2 by 2. If you follow our usual assemblage in the case of getting assembled element stiffness matrix, this will be of size 8 by 8. Now, for the structure, you have got only 5 nodes, 1, 2, 3, 4, 5. So, from this 8 by 8, you have to get 5 by 5 matrix because the global structure consists of only 5 nodes. So, from this, how to convert the 8 by 8 matrix to 5 by 5 matrix using direct stiffness method. That is what is called getting the global stiffness matrix. So in this example, you have to get 5 by 5, but actually you have got 8 by 8 value. 8. So what are the values that are to be fitted in various positions of the global stiffness matrix? How to assemble them? So that we will elaborate and discuss when we discuss about the particular step. Now let it be general for till we complete all the basic steps. So you have to understand now that we have to get 5 by 5 matrix. For 4 elements you have got 2 by 2, as before, suppose if you write, it will be 2 by 2, 2 by 2, that is K1, K2, K3 and K4, 2 by 2, you will be getting a 8 by 8 matrix. 8 by 8 is not wanted for us, we want 5 by 5 matrix. So, what are the values to be filled in various places of the global stiffness matrix? 5 by 5, that is what is called assemblage of a global stiffness matrix by the direct stiffness method. We will discuss through an example a little later. Similarly, getting the global load vector F. Now, by adopting either the direct method or variational method or whatever may be, now you know what is the force in this node, what is the force in this node, what is the force in this node, force in this node. Therefore, you have got 1, 2, 3, 4, 5, 6, 7, 8. You have 8 forces. You have got 8 nodal forces. Assuming one displacement per node, you have got 8 forces now. Each and every element, you have got 2 forces. Now, the total structure consists of only 5 nodes. 5 nodes. So, this 8 forces, you will have to convert as 5 forces. 5 forces. For example, we can say 1, 2, 3, 4, 5. Let us say this is 1, 2, this is 1, 2, this is 1, 2 for the elements, 1, 2 for the elements. Right. Now this is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 is the global numbering. This is a global numbering or structure load vector. Now for element number 1 contributes to load number 1. So element number 1 is this thing. Element number 2 contributes. This you call it as X. This is plus. For example, right. Now element number 2, node number 1 of element number 2 contributes to node number 2 of the structure. So therefore, that contributes here. This we will call it as into. So this is into. Now element number 3, 1 contributes to structure 3 and 2 contributes to structure 4. Therefore, that is marked with a plus. Therefore, this 1 corresponds to this 3. 1 corresponds to this 3. Therefore, this is plus. This is also plus. Now, this we will use hash. Node number 1 of element number 4 contributes to 4 of the structure. Node number 2 contributes to 5 of the structure. Therefore, this is hash. For element number 4, this is hash and this is hash. So these values if you add, so this is the contribution from, this is element number 1 only. Now for this join, element number 1 and element number 2 contributes, therefore the two values, this value, for this 3, element number 2 and element number 3 contributes, for this into, for this plus. So those values are marked here, similarly for node, similarly for 5. So when these values are added, you will get 5 values. This is what is called getting the global load vector or structure load vector from the element load vector. So that is what is called assemblage. So that is another important step, assemblage of global stiffness matrix from the element stiffness matrix, assemblage of global load vector from the element load vector. So that is, we follow direct stiffness method. We will further discuss this later through another example, right? So that's about the 5th step. Next step is that of introducing boundary conditions. Boundary Now you have got the stiffness matrix and load vector for the structure. From element to the structure we have moved. From part to whole we have moved. But before solving, we have got some points to be discussed. Now, next is introduction to boundary conditions. When we have assumed element number 1, we have assumed displacement node number 1, node number 2. Similarly, when you have taken element number 4 also, we have assumed displacement node number 1 and node number 2. So, as it is, the structure is not grounded. The structure is not grounded because all points we have assumed displacements. So, before going for the solution, the displacements are to be arrested at a sufficient number of coordinates of the system, so that the structure will be stable. As it is, when you assume displacement node number 1 as well as displacement of node 2, the structure will have a rigid body motion. The matrix will be ill conditioned. The matrix cannot be inverted. You cannot get the solution because the structure will have a rigid body motion because the structure is not grounded. Therefore, the structure has to be grounded. So, the displacements at sufficient number of coordinates are to be arrested. So, that is what is meant by introduction of boundary conditions. Now, for example, if you take this beam, if you vertical displacement, now the vertical displacement coordinate number 1 is to be arrested. Similarly, the vertical displacement, the coordinate number 5 of the structure is to be arrested. So, when these two are arrested, the structure will be stable. Suppose, if you assume two displacements here, suppose you take a hinge here, the horizontal displacement is to be arrested, the vertical displacement is also to be arrested. Similarly, roller support, the displacement perpendicular to the plane of rollers is to be arrested. So, you have to ground the structure so that the structure is stable. Then only your matrix can be inverted. That is what is called the introduction of boundary conditions. Otherwise, the matrix cannot be inverted. Now, for introducing boundary conditions, there are, because you must know why we have to introduce boundary condition. What is a boundary condition? Why you have to fix it to the ground? All those things you have to understand. Then there are number of methods. One is unit diagonal method. For introducing boundary condition, we have got unit diagonal method. We have got large diagonal method. We have got row column delete method. Row column delete method. These are the methods. Also, this is for introducing zero boundary condition. The displacement is 0, x direction, y direction, etc. These are the methods. Also, at a particular point, if you know the displacement is equal to 0.05 mm. For that also there is a method that is introducing, plus there is a method for introducing known value of displacement. Known value of displacement. For this we have methods introducing known value of introduction. So these methods we will discuss when we take up the individual steps. So that is about the next step called the introduction of boundary conditions. Next step is calculation of primary unknowns. See, we are following displacement based finite element approach. So we know that the displacements are the primary unknowns. Displacements u. Now we have gone to the structure stiffness matrix. We have got capital K into U equal to F. So already we have got capital K values and also F values for the structure we have got. Therefore, now you have to find out U equal to K inverse into F, because you know K into U equal to F, or U equal to, U stands for the system displacements, K stands for the system stiffness matrix, and F stands for the system forces. Now you will have to get the value of U. They are the primary unknowns. We are following displacement based approach. Therefore, the system displacements are our primary unknowns. So for solving this, you must know the numerical methods, various numerical methods. So for solving simultaneous equations, and also of course computer will solve everything, but still you must have an idea about the different numerical methods. Now, but when you solve, before solving, there are some properties of the structure stiffness matrix that you must be aware. What are the properties? Whether the stiffness matrix satisfies the properties. You know, in the structure, the non-zero values will be only along the leading diagonal. It will be clustered about the leading diagonal. All other values will be zeros. The values will be non-zero only along a cluster closer to the leading diagonal. So you will have values on both sides. All other values will be zeros. It will be clustered along the main diagonal. That is one property of the structure stiffness matrix. Number two, the stiffness matrix will be symmetric. Suppose you take K37 equal to K73. If it is K54, it is equal to K45. If it is K87, that will be K78. Both will be same. K12 will be K21. K45 will be K54. K63 will be K36. Like that, it will be symmetric. Therefore, there is so that is another property, because you are going to store only values above the leading diagonal or below the leading diagonal. The diagonal value plus the values above, or diagonal value plus values below, because symmetric. So you need not unnecessarily store one part. That will save your memory and also solution. There are solution techniques are available. Solution techniques are available to store only non-zero values and to solve the equation. Therefore, you will reduce the storage space. Therefore, you must know the property. So, structure, the system stiffness matrix will be a symmetric matrix. So, and another point is, all the values along the leading diagonal are positive definite. All values will be positive definite. So, these properties one must be aware. And using the, if it is a small problem, using the numerical methods we can solve. If it is 4 by 4 or 5 by 5 or 6 by 6, you can go for the numerical methods. But finite element method is not meant for solving 3 by 3 or 4 by 4. This is meant for analyzing complex structures. Your equations will be in the order of 800 by 800, 900 by 900, 1800 by 1800, like that. It is meant for computer. It is computer based method. So either using the numerical methods for small problems that you are usually solving in the class, or if it is a real structure, it will be a large number, maybe 2000 by 2000 also, right? So you have to solve the primary unknowns. Primary unknowns are the displacements. Before solving the displacements, you must be aware of the properties of the structure stiffness matrix. So you will get the value of U. You will get the value of U. You got the this. We have got it in the fifth stage. In the fifth step, you have got, and you will be able to get the value of the system displacements. Then after this, calculation of secondary unknowns. So secondary unknowns. For getting the secondary unknowns, what you do is, now just we have taken a beam with the 5 nodes. We have taken a beam with the 5 nodes. 1, 2, 3, 4, 5 nodes. So this is 1, 2, 3, 4, 5. Assuming one displacement per node, we got 4 elements. 1, 2, 1, 2, 3, 4 elements. This is 1, 2 for element number 1, 1, 2 for element number 2, 1, 2 for element number 3, 1, 2 for element number 4. Now, calculation of secondary element, secondary unknowns, again we are going back to elements. From elements, we have gone to the structure. Up to the primary displacements, we have concentrated. Now, we are going back to the elements. Elements, suppose you want to analyze element number 3. Element number 3. You know the stiffness matrix for element number 3 already, that we have got it in the third step. Now, we have to find out the strain. Strain epsilon is equal to B into delta. Epsilon equal to, this is element strains. This is element strains. This is the matrix of element coordinates. Already we have discussed B matrix. B matrix, a matrix of element coordinate. If it is a triangular element, if you know x1 y1, x2 y2, x3 y3, you can find out what is B matrix. Anyway, we are going to discuss the derivation of B matrix for one element later. B matrix is already known. This we have done in the third step, right? Now, delta is the element displacements. Now, element displacements you have to take, if you want to analyze element number 3, you got 2 nodes, node number 1 and 2. So, the element displacements correspond in the system is 3 and 4. So, you will have 5 displacements, U4 and U5 you have to take. So, for this, delta equal to, you have to take U4 and U5. So, U4 will be delta 1 for element number 3, U5 will be delta 2 for the element number. So, this is for the system, this is for the element delta 1, delta 2. So, you have to take U4 and U5 and substitute here as delta 1 and delta 2. If you want to analyze this element number 2, for 1 this is 2, for 2 this is 3. You have to take U2 and U3, that you have to use for element number 2, epsilon 2 equal to the B value corresponding to element number 2, and delta value will be delta 2 and delta 3. Like that, you have to pick up the corresponding displacement from the system displacements and use it for getting the element strains. So, that is element strain. So, from the displacements are the primary unknowns. From the displacements, you get the element displacements and find out the element stiffness, element strains. So, from you get the delta, using delta you get epsilon. So, this is the strain. Now, from strain, you can stress is equal to d into epsilon. If it is a two-dimensional structure, your epsilon will be consisting of epsilon x, epsilon y, gamma xy. Your epsilon x will be dou u by dou x, epsilon y will be dou u by dou y, gamma xi will be dou u by dou y plus dou v by dou x. You can get the displacements if it is this is for a two-dimensional structure. If you know u, if you know v, dou u by dou x, dou v by dou y. If you know u, if you know v, you can differentiate and get the strains. That is in this step. This is for a one-dimensional structure. If it is for a two-dimensional structure, you will have to find out epsilon x, epsilon y, gamma xy. You know the displacements, u, v, in this step, you got all the values here, all the values here. Using those values, you can get the strains. If you know the strains, you can get the stresses. D is the elasticity matrix. So, elasticity matrix in the finite element library, elasticity matrix will be available for a plane stress element, plane strain element, axis symmetric element, 2-dimensional, 3-dimensional, everything it is available. I will tell you later what is elasticity matrix, how to derive the elasticity matrix for a simple case. So, this is available in the finite element library. So, that connects the stresses and the strains. So, how to derive the elasticity matrix for one simple case we will discuss in the future lecture. So, D is the elasticity matrix. So, this is the elastic. So, this is available in the previous step. Using that you can get the stresses, and once if you get the stresses, you can get, that means suppose if it is two-dimensional, you will be getting sigma x, you will be getting sigma y, you will be getting tau xy. Sigma x, sigma y and tau xy for a two-dimensional structure. Once if you get sigma x, sigma y and tau xy for a two-dimensional structure, you will be able to get the principal stresses sigma 1, sigma 2, tau max, theta 1, theta 2, using your basic knowledge on strength of materials. So, that will give you the principal stresses, and whatever stresses you want using the basics of strength of materials and also what you have studied in theories of failure, you will be able to find out anything. So, the primary unknowns are the displacements. From primary unknowns, strains and the stresses are the secondary unknowns. So, this you have to extract values from the global displacement vector and get the values for the elements, and from that technique is available. What is the force inside the element, what is the displacement inside, at any point you will be able to find out. Initially you will be dealing only with the nodal forces and nodal displacements. Later, after getting all these values, there are techniques which will give you the values at any point, the displacement at any point, the force at any point, you can easily find out. That is about the basic steps. Actually, if you want to analyze a beam, if you divide this beam into 4 elements, suppose if it is subject to the UDL over the entire span, you know that the bending moment diagram will be a parabola having a maximum value of WL square by 8. If you divide this into 4 elements, actually you will have some bending moment here, some bending moment here, some bending moment like this, the bending moment diagram. You will get the bending moment diagram. The same thing, you divide into 8 elements, this value will be less. So, like that, the accuracy will be a little better. This value will be less. If you go for 16 elements, 32 elements, so this value will go on reducing. This value will also approach the true value. Therefore, more the number of elements, better will be your accuracy. So, it is a numerical technique, it will be approximate. If you go for more number of elements and more order of more values of the polynomials, your results will be more and more accurate. So, that is about the introduction to the, these are the various steps. So, from part to whole, that is the principle, and the basic principle is principle of discretization. And later we will discuss one by one, subsequent from next lecture onwards, we will discuss the steps one by one. But before concluding, the points are, so the finite element method is advantageous. You can incorporate or many or different properties for each element. You consider a triangular element, the triangular element can be of 3 or 4 different materials, maybe 100 mm thickness, first 20 mm may be one material, second another 30 mm may be different material, third layer, fourth layer. So, each and every element you will be able to incorporate different material properties. So, that is one advantage. And any degree, whatever may be the non-homogeneity, that can be incorporated in finite element method. And similarly, no restriction to the shape of the medium, because normally, now suppose if we are given a simple beam subjected to some loading UDL or point load, we will be convenient in analyzing the structure by our simple strength of materials. Suppose the same beam is subjected to uniformly varying load, that also we can analyze. Now the same beam, suppose if it is of varying cross section itself varies from I to 2I, and it is subjected to again some varying load. The analysis is very tedious in strength of materials. Uniform beam subject to uniform loading or a point loading beam will still be convenient. So more and more complicated means now in finite element analysis, the beam can be like this. The beam can be some irregular structure. The structure may be having any irregular boundary. Anything is possible. Any boundary condition is possible. Any non-homogeneity is possible. So that is the advantage of finite element analysis. Any type of boundary condition, non-linearities, arbitrary loading, time dependence, anything can be incorporated. It is applicable to wide range of problems in engineering and also mathematical physics. So these are some advantages of the finite element method. And coming to the disadvantage, if proper physical comprehension or physical interpretation of the problem is not possible, then this will not give the true result. That depends. Now there are many chances for the solution. The K matrix will be singular. If the K matrix is singular, then a solution is impossible. So configurations, element sizes, violent variation in the element size. It is one end, you start with 10 centimeter by 10 centimeter element. The other extreme, in between, you have 100 by 100. The other extreme, 200 by 200. That violent variation in the size, if it is there, it will be difficult. Violent variations. Boundary conditions, if you are not introducing sufficient number of boundary conditions, then the solution will be difficult. And also units. For dimensions, use meter. For stress, if you use Newton per millimeter square. For moment of inertia, if you adopt millimeter to the power or centimeter to the power 4, then it will be a problem. So unit you will have to consistently follow the same units. If these things are not properly followed, the matrix will be singular. The matrix cannot be inverted. You cannot get a proper solution. And also proper checks are needed, because in the case of any software, not only finite element, any software that you use, proper checks. So you have to apply to some known problem. Whether you take steel structure or RC structure or pre-stressed concrete structure, whatever it may be, there are a lot of worked examples in the books. So you can apply the finite element method or STAT Pro or whatever may be the software that you use. You have to apply to known problems. Few problems apply. Different types of loadings, different types of structure. For known problems, you just apply. You find out whether it gives the correct results, or what is a mistake on your part, or what is a mistake on the software part. That you have to properly analyze, confirm that this is how I have to introduce the loading, this is how I have to introduce the boundary conditions, this is how I have to divide the structure. Like this, you confirm by applying to a known problem and then go further solution, because there are many softwares available in the finite element library. Finite element softwares, varieties of softwares are available. In the software, particular software, varieties of elements are available. So you must know what is the software, what are its features, how you have to introduce the values, what is the order in which you have to introduce the data. If you do all these things in a proper fashion, you will get the correct result. Because otherwise, software, any data if you give, if it requires 100 data, if we say 1, 2, 3 to up to 100, it will give some results. But it will be of no use to us. So No, you must know what is the order in which you have to give the data, what are the data that are to be given. You have to be careful with the units. Only if you do all these things, you will get proper results, convergence, everything. So otherwise, garbage in, garbage out. You will not get the required results. So you have to be very, very careful in the usage of the softwares. So this completes the fundamental steps in the finite element method. So to summarize, one is divide the structure into number of elements, assume the displacement over each and every element that is considered, displacement variation or displacement. Third one, derive the element stiffness matrix from the equilibrium equation. First you have to derive the equilibrium equation, derive the element stiffness matrix, then element load vector delta. There are some methods. Then using the element stiffness matrix and element load vector, using the direct stiffness method, you get the global stiffness matrix and a global load vector. Then you assume displacement at all points, so you have to introduce sufficient number of boundary conditions. You have to ground the structure so that it is stable. So that is what is called the introduction of boundary conditions. There are three methods for introducing boundary conditions that you have to, one of the methods you have, any one method you have to use. Then go for the primary unknowns, solution for the primary unknowns, and then using the primary unknowns, getting the displacement for the particular elements, you have to get the element strains, element stresses, whatever may be the principal stress, principal strain, whatever you want, you can just calculate. That is secondary unknowns. Then you got checks, primary checks, and all those things will be, because if you take two elements, the stress here may be 5 Newton per mm square here, the stress may be 7 Newton per mm square. At the same point in the second element, the stress may be 8 Newton per mm square, the stress may be 10 Newton per mm square. For this there is a reason why this is 5 and 7 for this, and why it is 8 and 10 for this, why at the same point you have got two different values. For those things you have got reason. There is, you have to adopt some smoothing technique and all those things are there. That is beyond the scope now. We will discuss the required points at later stage. So post processing, that is also there. So this will give you the required points about the basics of finite element method. In the subsequent lectures, we will go for the individual steps one by one, along with some numerical examples. Thank you for your patience. Thank you. Karthi.